situations. So we're going to talk about earthquakes today. Before we get too far along with earthquakes, what I'd like to do is remind you just briefly that the first exam for the class is going to be this Friday, September 18th, officially. Just to give you a setup on what to expect in the exam, it's largely going to be true, false, multiple choice, short fill in the blank questions, very much in line with types of and styles of questions you're getting on the worksheets online. Just in case anyone's concerned about the timing or the date, just remember I'm going to post the exam, set to post already at midnight on Thursday, and you'll have a full 48-hour window which to complete the exam up until the end of the day on Friday, and probably I'll make it just a little bit later just to make sure everyone has a ease of use in the first time through doing this on this course. Again, the exam will be online. It'll be very much in the same format as everyone's been using for the worksheets. Everyone's been doing very well, and I hope to see that continue on the exam. Once the exam's open, the only caveat in terms here is that once the exam's open, you'll have 2 hours to complete it, or if you've arranged with me to have a longer period of time for various reasons, then you'll have longer, and that's not a problem. Take as much time as you want. And then what I was also going to bring up is that before the end of for tonight, I'll send out a written sort of exam review with key concepts and questions that I might include on the quiz. Although in reality, mostly looking at the lecture notes, almost exclusively looking at the lecture notes and looking at the quizzes I provided are a good strategy to do that. I'll add some additional quiz type questions which will be good hints to have on the review sheet. And then on Wednesday, at the very beginning of the synchronous lecture, I'll spend about 20 minutes conducting a sort of a review of the key concepts and the key questions, and have a little bit of question and answer before we go on with lectures. So anything in the lectures, anything on the worksheets is fair game. If you spend a lot of time with those items and you study them, I think you'll do very well. I don't have any concerns. Everyone can hopefully get a perfect score. As far as I'm concerned, that would be fantastic. In terms of material, I'll just to word off the questions I'm sure I'll start getting soon is that we're going to lock the material up through to this afternoon's, up through to the end of today's lecture. So what I post this afternoon, or hopefully later this morning, in terms of this recorded lecture, will be the end of what's going to be on the exam. Although it'll be more focused on things from the beginning of the semester till now, rather than trying to cram things at the end here. So I wouldn't worry too much about it, but definitely just keep in mind what the schedule is for the quiz. So for the quiz, I got a question about how many questions. There'll probably be something on the order of 25 questions, 25 to 30 questions usually. I haven't finalized it yet till I see how far I get today, but it's not going to be 100 questions. There's no reason to have a lot of stress about it. You don't have to answer very quickly. You'll have an adequate amount of time to do it. The other component is, just like the worksheets, you'll have 2 chances. So it won't tell you if you got it wrong, but it'll give you a chance to change your mind on those different things. And you should have plenty of time to do it, do the exam without any concerns. So I'm not going to take any other questions on the exam right now. If you have them, let me know. I'll answer your questions after class. I won't spend more time talking about it now, but I will cover it in the review on Wednesday. We can have all kinds of time to discuss if everyone's content. But I think in general, as everyone's been doing well in the worksheets, I have no fear that anyone's going to have trouble being successful on the exams. They're really just more comprehensive versions of the quizzes. One other thing I was going to say, just to word off some questions. Obviously, we're happy to have them email me. Go ahead with questions, but people will ask me, is it allowed to be open book? And the reality is, rather than trying to find some imaginary way to police that, you're more than welcome to keep your class notes or whatever you want with you for the exam. We don't normally do that, but I think in this scenario, I'm perfectly okay with it. So, we'll cover more details on Wednesday. If you have any questions, email me. I'm happy to give you some answers. So, in getting back to earthquakes and talking about this, I was going to bring up some questions, bring up some discussion of the earthquakes. We're going to get into. We're probably going to go on to wrap up earthquakes in the next week after the first exam. So some of the questions we're going to get to as part of this earthquake discussion is, what processes are responsible for earthquakes, for faulting? Where on planet Earth are earthquakes most prevalent? what are their impacts, why do they cause so much damage, and what's all the sort of the basic science behind the fact that these rocks break and send distribute energy and shock waves around the Earth. What kind of damage specifically they cause? What are the risk factors? How can you, if you're about to buy a home, for example, in a new location, how can you assess whether there's any real risk for earthquakes in that area? And then, and then where we're going to wrap up with that really is how much does human activity actually affect earthquakes? Can we, can we have some component in sort of sealing our own fate with regard to how common earthquakes are or the level of damage they do? Is there anything we can do about them to predict them? So I'll start with some basic facts. How many earthquakes can be felt by people each year? For perspective, that's about 1 million earthquakes a year that can be felt by people somewhere on Earth. I'm going to switch my screens briefly if this goes well. I hope it does. And I'm going to try to share with you some material about some recent earthquake activity in Yellowstone National Park. So I got some questions last week about supervolcanoes, and hopefully everyone can see the screen. If not, let me know. But just some headlines from the news in the last few days. Over the weekend, actually on Friday, Thursday night and Friday, there were over 90 earthquakes, which has now been well over 100 earthquakes within a 24-hour period in Yellowstone. And even though these are all felt, these are one of those millions of earthquakes felt every year. The key thing here is that there's no reason to believe it's evidence of an imminent eruption in this case. It's probably nothing to worry about, and in fact, most people recognize it's a fairly common activity where episodically throughout the history of Yellowstone, there's been these periods of intense activity. So about 1 million a year are felt on planet Earth. Most of these are felt very close to the source. The Yellowstone example is a perfect example of this, where folks living in southern Montana, northwestern Wyoming, Idaho actually felt them. Very, very mild earthquakes in this case, but really they're not in general commonly felt any further away than that. And then earthquakes, as I think most of you probably know, the way we actually classify earthquakes is according to their energy of release, and that's called the magnitude. The magnitude is the amount of energy released during an earthquake event. Although there is a growing need in terms of better aligning our characterization with the hazards they create, thinking about them in terms of the intensity of shaking, which is the ground motion. Most commonly, though, the magnitude is the amount of energy released during the earthquake event, and that's what's usually used to describe them. You'll hear, magnitude something earthquake, for example. So just give you a little sense of major earthquake activity in the United States in the last few decades. These are just looking at relatively large earthquakes. Notice that most of the earthquake activity, they don't even show the eastern part of the United States, but most of the earthquake activity is along the western margin of the United States. Going back to those plate boundaries we talked about in the last class, many of them are along the San Andreas Fault, which is the transform fault between the Gulf of California right up through Central California here, or along the Cascadia margin where there's a subduction plate, a convergent boundary that's coming towards North America. Same thing is seen here in terms of out of here along Mexico, western border of Mexico, and near the sort of plate boundaries. So the key thing here is that most of the earthquake activity is along plate boundaries. But what might surprise you, and we'll spend some time talking about today, is notice there's been some major earthquakes in the last few decades, actually in the central plains along the Mississippi River area of the United States. We'll talk about more throughout the lecture today and later in the week, so you'll understand what that is about later on. So some key terms we want to introduce here in terms of earthquakes. The sort of most important term is something we call the focus, and the focus is basically location of rupture on the fault plane started. This is where the initial stress built up to the point where that location started to actually move, and then the rest of the rock is displaced as that energy is transferred as part of the earthquake event. So again, focus is where the rupture started on the fault plane. So that's notice going to be at some depth below land surface. Usually you can't build up enough pressure, enough friction, and overburden pressure really close to the surface. So you can't really have earthquakes originating near the surface. They have to be under some lithostatic pressure, under some weight of the overlying rocks. develop enough force for there to be a focus area. So the focus will be at depth below, the point on the surface below where below the surface where the rock fractures or ruptures. And the epicenter, which is what we usually actually see projected onto maps, on the news talking about earthquakes, is the point of the surface where that focus projects to the center, the surface of the Earth, or the center of the surface of the globe. So the epicenter is often sees most of the energy that reaches the surface is very close to the epicenter, and the amount of energy that's observed at the surface, of course, dissipates in general out away from the epicenter. But those key terms, focus and epicenter, are two things I want you to know. You'll see them identified on your worksheet, and probably they're a good idea of the type of question I'd ask you, to understand what epicenter and focus are. There's some other terms here, but so the focus and the epicenter are sort of intrinsic facts of earthquakes. There's always going to be that information. Another common feature is sort of the surface rupture, which is we call a surface rupture, or a SCARP, SCARP, and that's basically the amount of displacement of two bodies of rock, on the surface. There's not always this isn't always the case. You don't always see actual rupture on the surface, but it's not uncommon. And the key thing here is that this sort of curvilinear, nominally planar, although the faults are not perfect planes like we show in this picture, but this surface between the two bodies of rock that either rupture or fracture apart is basically called a fault plane. Okay, so this one is an up and down arrows here, with that plane that you could imagine sliding between those two things is the fault plane, which is shown here with the arrows. And then these directions will actually tell you fault slip. In this example, it's a sort of a vertical up and down. You don't need to know this, but that's called in geology a normal fault. But those plates, if you think about transform boundary, they can move past each other. In this case, the arrows will be going in different directions. Or in some cases, it can be called a reverse fault, where the bottom thing will slide up, which will allow you to look at in that case, this block will be going up and this one will be going down. So, I'll encourage you to make sure you keep this slide handy if you're going to look at your notes during the quiz. I promise you, or the exam rather, I promise you that some of these terms will reemerge on Friday, or whatever time you choose to take the exam. Key thing here is that the moment magnitude is a measure of the energy released at the focus during the time of the earthquake, and that's going to be the key characteristic in determining how powerful it was, or basically how much force it built up before the rock ruptured or fractured. Historically, this moment magnitude was measured in something called a Richter magnitude, the Richter scale, and that was used previously to describe the amount of energy. And this was named after the seismologist Charles Richter. And that's something it's actually not commonly used today. It's been replaced by the moment magnitude, the total amount of energy, in about the 1970s. But if you've heard any earthquake news on the radio or the television, you no doubt often still hear people say something like it was 6.0 on the Richter scale. And actually, what the number they're quoting now is not really the Richter scale anymore, but actually the moment magnitude, of the earthquake's energy. And the key thing is that it's based on the amplitude, or the size of the largest seismic wave from Richter. So Richter's scale was still logarithmic, where a magnitude 4 earthquake was 10 times bigger than a magnitude 3 earthquake. But his characterization is based on the amount of energy deduced by the largest wave that came off of there. Larger seismic wave, now it's based on the total amount of energy, which is much more accurate scenario, because sometimes the amount of energy can be distributed over longer periods of time. Some key ways that we actually investigate these processes. The key instrument here is something called a seismograph. I think probably everyone is fairly aware, I've heard of that before, aware of it. And it's an instrument that records the amount of displacement and waveforms on, in different types of waves, which we'll get to in a second. And they're recorded sort of with these seismic lines by looking at the attenuation of different energies. That's what you see in the gray in the background here. And so this would be the very earliest part of the major seismic waves that we'll talk about more as we go on today. Just like the moment magnitude that's used now, the Richter scale again is logarithmic, and as a result, 7 is 10 times greater than 6, or 4 is 10 times greater than 3, as we mentioned. To give you a perspective on earthquakes, the Earth is a very active and dynamic system, as we've kind of alluded to already. Worldwide, these numbers are from 2000, but they haven't really changed much at all. They're pretty much the same. But to give you a perspective, although I said there's a million earthquakes we can feel, there are millions and millions of what we call microseismic events, or events that are small enough to be below the threshold of about 2 to 2.5 on the earthquake scale here, that aren't really even felt without the presence of seismographs. So, but for some perspective, great earthquakes, which are magnitude 8 or higher, so 8, 9s, and 10s. There's about one event a year. That's sometimes there's 2 in a year, 3 in a year, and sometimes it's not one for several years. But for the perspective of the greater events, these are pretty infrequent. I can think of just a few dozens from my lifetime, but usually these are ones you hear about and occur relatively infrequently. Major earthquakes are several times a year, obviously 18 times per year. You hear about major earthquakes. Strong earthquakes. Notice that as we're going down this list, it's almost an exponential increase in the frequency at which they occur. Strong earthquakes, magnitude 6 to 6.9, are felt over great distances, cause ground disturbances and can do a lot of damage. And then mainly, although they can still do a lot of damage even when they're smaller, mainly once we get into the moderate and certainly the light, minor, very minor events, these can become incredibly frequent, up to 50,000 per year in the minor range, or very minor, thousands per day. And then the microseismic events, less than about 2.0 on the magnitude scale, are basically continuous. If we were all on campus, I could jump up and down in class and actually produce a 1.5 magnitude earthquake that could be felt on the seismograph that's in Mendenhall, where we would normally be meeting here. But key things here is that with increasing magnitude, there's a much rapid decrease in the amount of events per year. Although clearly, basically anything from about a light earthquake about 4 up to greater has potential to do damage. And we'll take you through a lot of the aspects during today's lecture and later this week as to what dictates whether there's going to be damage in your local area. What you might not have seen before this class at all is a sense of what the relative hazards are for earthquakes. So I gave you an example already about Yellowstone here. You notice that that's in a pretty moderate to high hazard area. Most of that seismicity is actually tied to movement of magmatic and volcanic fluids in that area, which can cause ground disturbances and rupturing and fracturing. But I don't think it'd be a terribly big surprise to any of you that most of the highest hazard areas in the country are actually along the west coast of the United States, from the Gulf of California up along the San Andreas Fault into Northern California here. What I think might be a surprise to many of you is that the equivalently highest risk area is actually sort of in the area of Memphis, Tennessee, southern Missouri, right along the Mississippi River. So if anyone has heard about this, I'd love to know. But most times this is actually a totally new idea to people, that there's major risk areas. Another example of this is actually on the Atlantic seaboard in the area of South Carolina, North Carolina. If you were paying attention, about 6 to 8 weeks ago, there's a major seismic event in Raleigh, North Carolina. Not in Raleigh, but in central North Carolina, up in this area. For perspective, if you're thinking about geological risks such as earthquakes, a lot of people don't realize this, but the United States Geological Survey has 2 seismic risk stations. One, not surprisingly, is in the Bay Area in California, Menlo Park. The other one is actually up here in Buffalo, New York. And in all cases, these eastern seaboard and central plains earthquakes have actually produced incredibly large amounts of damage and can cause a lot of damage, both to humanity and infrastructure. This is I'll take you through these other areas just really briefly. This is actually the Great Lakes here, but as you move through the Great Lakes, this becomes the St. Lawrence Seaway, which actually runs all the way out into Canada, eventually into the North Atlantic, and that's actually a paleo rift zone, an area where there's a divergent plate boundary that sort of failed, but there's the plate is broken apart in those areas, and that area in itself actually has been both faulted, but also has really large amounts of sort of like sediments that never got lithified. And as a result, this area has both really high magnitude earthquakes, magnitude 6 within the last decade, number 5.8 within the last decade, but also has underlying rocks that are not really lithified as rocks; they're just sediments, and as a result, they can sort of be disturbed really easily. Similar idea here in along the Mississippi River. Most of the big rivers actually follow fault traces or often follow fault traces, and that's certainly true along this area. This is another example of the continents. We talked about the plates accreting and building more and more big continents and then diverging apart. Well, this area was a place where two different plates, two microplates came together. There's an old suture zone where those two plates got put together, and that when Pangea broke up, that tried to break apart and never really did. But as a result, there's a plate boundary. There's no plate boundary, but there's actually a lot of fracturing and faulting when that plate tried to break apart and create a plate boundary. As a result, there's an incredibly active amount of seismicity in this area. And the same thing's actually the scenario over in South Carolina here, or off the coast of South Carolina, where you have scenarios where the plates get put together that has a boundary when it's put, they add more and more pieces on. And those boundaries, while they eventually sort of get amalgamated to one big North American plate in this example, they actually have sort of paleo fault zones that are sort of zones of weakness that can sort of break apart and at least have a lot of fracturing and faulting that leads to seismicity. So I'm guessing most of you didn't know about this. If you had, good on you. Today, the U.S. Geological Survey and the Department of Defense rate this particular hazard as one of the biggest single hazards, seismic hazards facing the United States. There's something like 8 or 9 nuclear power plants, within this region, all along the Mississippi River. And for perspective, talking about major earthquakes, there have been, as recently as 1811 and 1812, there have been many magnitude 7.5 or above 8 earthquakes, some major and great earthquakes in this area. And we'll talk about this a bit more in a minute, but it's considered to be an area of major potential risk in the future here. So some general earthquake definitions. Okay, there's the interplate earthquakes, and basically these are the interplate earthquakes, the ones that occur between two different plates. So in the case of San Andreas, where you have North American plate sliding past the Baja California, you can see there that that's an interplate where the earthquakes are between the two plates and initiate along a plate boundary. That's the most, by and large, the most common. So most large earthquakes are interplate earthquakes, particularly around the Pacific Ring of Fire, where you have subduction and transform, so convergent and transform plate boundaries all around the Pacific. The number of interplate seismicity there is quite profound. You can see in the background here the amount of seismicity around this Pacific Rim of Fire with both seismicity and volcanism. The alternative to interplate is intraplate. So intraplate is where large earthquakes can occur within a single plate, and these are most commonly associated with those areas of failed rifts where there was an attempt to tear things apart, and there was fracturing and faltering in the upper part of the crust, but the plate never really separated. So it's still within a plate, but has some faults that are really active, and interplate volcanism or interplate seismicity. So I apologize, keep using the wrong word there. It's largely because our next lecture is about volcanism, and then they both tie to some of the same concepts. So I apologize for my slip up there. But interplate earthquakes can occur, within a single plate. So here's a more detailed view of the map. I sort of alluded to this already, but notice that if you look at this map, you can see that clearly most of the seismic events are along these plate boundaries. This outlines the Pacific Ring of Fire, or Rim of Fire, as it's alternatively called. And notice these are all where convergent plate boundaries or transform boundaries sort of make up the difference there. A lot of seismicity is also along plate boundaries and the divergent boundaries. Those tend to be much lower magnitude, but where the plates are being pulled apart and magma is getting in place, that causes some fracturing, faulting, and can cause seismicity. And then most of the other seismic lines you see here basically highlight areas of similar processes in other parts of the world. So a little bit more detail on this New Madrid fault, as it is. It was known, it's called that based on some earthquake activity that occurred with a epicenter in New Madrid, Missouri. So right smack in the middle, right on the Mississippi River. This was a location of magnitude 8 I think 7.5 to 8 earthquakes in 1811, 1812. And it's certainly been an area of active seismicity for the last, continuing for the last 200 years. These earthquakes destroyed the town of New Madrid. killed an unknown number of people in the 1812 earthquake. Give you a perspective on this. This earthquake was so large, the seismic waves propagated so far that church bells were ringing in Boston, in 1812 as a result of these earthquakes. The Mississippi River, there's so much of a fault scarp that was formed where the Earth's surface was deformed. The Mississippi River actually flowed the wrong direction, where the Gulf of Mexico, the Gulf of Mexico end of the Mississippi was actually running back into Missouri and flooded out quite a lot of the area around there. So some questions you might want to ask is, why is the interplate seismicity here and specifically, and what is exactly is causing this to occur? So I mentioned the fact there's a failed rift, but the key aspect here, and it's a little bit difficult to explain without an image, without being there in person, is that attempt at rifting or creating a divergent plate boundary creates these sort of what's called Horsten grabens, areas where the rock is sitting there as one flat unit, it starts to pull apart, and that part just caves in on itself. So this is the graben that actually, and the Horst are the high parts, the low parts of the graben. I won't test you on those by any means. But what happens, it makes this particularly dangerous. It's not that you have an area that there's going to be faulting and potential for more seismic activity, but that the sediments tend to fill in on top of that really rapidly. And they tend to be wind-blown or water-blown sort of debris, and often it gets poorly sorted and doesn't get really well lithified. It just sort of gets filled in with loose sediments. And when water levels increase, or if seismic activities with water and sediments cause agitation, you develop this scenario called liquefaction, where that rock actually just sort of flows wherever, from a high surface to low surface. And as a result, you can see really large amounts of energy displaced and a large amount of fault scarping and change of surface levels, which of course lead to a great amount of damage. So, and commonly in areas where there's rifts or scars that formed, this one actually formed during the breakup of Rodinia. So even before there was life on Earth, back before the Cambrian, is when this formed. It's been continuously reactivated, or tried to reactivate, even until to this day. It never really got going. But to give you some perspective, I mentioned the number of nuclear power plants and other infrastructures, major cities like St. Louis and Memphis along this area. Give you perspective in terms of the risk. The new forecast is about a 7 to 10% chance that in the next 50 years, so 7 to 10, 1 in 10, 1 in 12% chance within the next 50 years of a repeat of the major earthquake like those that occurred in 1811, 1812, and they expect that would be a magnitude of 7.5 to 8.0. So in addition to the fact that we'd expect to see church bells ringing in Columbus and Boston, could you imagine what an event like the reversal of the Mississippi River would do to commerce, to flooding, to damage? This is something where I'm not saying anyone should be awake at night worrying about it, but we certainly need to be planning to build infrastructure that's actually resistant to an earthquake like this. And there's certainly potential for great serious disasters. So I'm not saying there's going to be a Fukushima type event here. But for perspective, this is, the tsunamis did a lot of damage to the Fukushima nuclear power plant scenario. But this is certainly an area where we want to make sure we build infrastructure in the right way and consider the fact that this has a reasonable potential to happen. Some of the questions you might add, is, for perspective, even though it's an order of magnitude less, that means there's about a 1 in 4, almost to a 1 in 2 chance of a magnitude 6 in this area during that time. That's a pretty large earthquake. It can do some serious damage. So one might ask, how do we come up with these forecasts? Where do we come up with this estimate of X amount of chance in 50 years? Earthquake prediction has notoriously been a science that hasn't really evolved very much. Everybody has an interest in of course, making sure we can know when earthquakes are coming, but in reality, we're not there yet. But one of the main, there's a lot of contributors to this. One of the main things is looking at the amount of microseismicity, amount of plate motion that's occurring there. Looking at the stress field, or how much force is building up that has to be dissipated. So you think about this as two objects flying past each other. They hit. There's some friction. If it's sort of well lubricated, they move past each other, and you might see a bunch of really small earthquakes. But if you sort of move in and lock and build up a lot of forcing, and then release it all episodically, you can imagine that would be a great force there. And people are working a lot trying to determine those sort of stresses, as well as more modern science looking at geodetic and satellite imagery, where they can look down and see where the surface is sort of building up stress and they're moving a lot. So it's an area of active research. a lot of people working in this, but it's an area where, within the the Midwestern, U.S., within the mid-continent of the United States, there's a real seismic crystal that most folks weren't aware of. Of course, these can be, major events in a lot of different directions. I'm going to try to show you a video here. I think I have to pop out of this here. So let me know if everyone can hear this, but this will give you a sense of what would happen in a magnitude 8 earthquake in. I'm sorry, this video does not seem like it's willing to play. I'm just gonna skip over the video. I'll post it online and try to look at it later, but it'll give you a sense of what a magnitude earthquake looks like inside the house, and I'll post this out on a message after class. So let's get into a little bit of the mechanics of how this works. There's some terms here that I want to make sure you know. If you haven't seen yet, they'll show up on your quiz. But there are two key sort of parts of this sort of forces building up around seismic events or earthquakes, and they're called stress and strain. And we all have an idea what stress is. We feel it in our lives. Certainly, in the last several months with COVID and whatnot, we have different kinds of stresses. But geologically, these have very specific meanings. So stress is the degree to which materials feel external forces. So if you have two bodies and they're just sort of slowly moving past each other, it's not nearly as much stress if they try to move past each other really quickly, or if they lock up and stuff like that and build up, additional forces. So obviously, the greater the forces, that are at play, can increase the amount of stress. And then strain is how the physical bodies respond, or to the degree to which they respond, deform, or change following the stress. So there's this excuse me. There's this definition a term I've introduced here that I want to make you aware of. It's common in geological science. It may not be terribly common in regular life, which is deformation. That's the amount of change in physical shape or in characteristics of a body as a result of strain. So an example of this would be fracture, breaking, or rupture. Another example in terms of change of characteristics is you can see metamorphism, one type of mineral to another. And this is called a Young's moduli. You don't need to know this for this class by any means, or the Young's modulus, which is basically compares the stress, the degree to which materials feel forces, to strain, or the degree to which they respond. And what you see in general is that as you increase the amount of stress, you increase the amount of strain. And then there's a point here where this becomes like the yield strength, where actually more stress doesn't actually increase it will just lead to rapidly increased amount of strain. So what you're talking about here is usually either something bending or breaking, becoming, depending whether it's brittle or ductile. I'll talk about that in a second. So the key aspect here is whether we know when we build up forces or build up stress in rocks, we know that's going to lead to strain. The real question becomes whether that's going to be a brittle or a ductile failure. And these are two new terms, again, introducing to you here. But the simplest way to think about this is if you took a plate, I think we all know as we drop it on the ground, it's brittle, it's going to break. So, something that experiences, brittle behavior will basically cause as stress increases, you'll see it fracture or fault. Okay, so that's often what rocks will do. And the alternative, of course, is ductiles, or if you think about something like a dough or silly putty or something like that. If you drop that, it'll sort of deform. Even if you put a high amount of stress by increasing, book or something like that behind it. The key aspects of these is that if you increase the stress on something brittle, it'll just fracture and fail. Something that's ductile can deform, bend. These can lead to things like faults. The first leads to typically faults. The second leads to folds or metamorphism, which can change the way rocks evolve. Key thing there, I want you to remember, these three terms are all fair game. I won't ask you to write them all down. I might ask you to true or false or multiple choice the right definition of these things. But I want you to remember that the increase in the amount of external forces is stress, how it responds is strain, and physical changes either in the metamorphic sense or in the shape is deformation. So how do these faults actually work? What are the processes in which they come? The key thing about an earthquake is actually the formation of a fault, the rupture of rock, which can occur, in some cases in a simply along a fault plane. More often occurs by series or networks of fractures or faults, microfaults that can become a larger propagated fault in the end. So the easiest way I can conceive to think about this is that imagine two by fours or pieces of wood sliding past each other. Obviously, friction causes, the imperfections in the surface cause plate motion to slow, or in this case, the example, the wood motion to slow. Some small minor pieces break off or catch along the plane of the other, and as a result, you see sometimes episodic motion along these areas. Clearly, similar is true for plate boundaries. Movement is slowed by friction of the rocks along this plate boundary that can lead to fracturing, presence of smaller faults or metamorphism, and clearly all of those occur in geology along fault planes. But whenever the stress exceeds the Young modulus, or the strength of that rock, it'll fail either by brittle deformation, which causes a rupture, or if it's still, if it's something that's not quite as hard, you can see it start to sort of bend or to metamorphose, which is sort of more ductile failure. Mostly, what we're concerned about with earthquakes is the brittle failure. Okay, here, and in any situation, we can, you always probably heard as a child, bend but don't break, and reality is that most rocks are hard enough that with enough pressure they'll actually eventually break and lead to an earthquake. So, what I want to make sure you think about here is we showed you that image of a fault being a plane. Realistically, what I want you to make sure you recognize is actually a fault is a fracture system. It's a series of fractures and smaller faults. But the key aspect here is when you talk about something brittle, when something breaks, that's a fracture. Okay, when that fracture moves relative to each other, when there's movement of that fracture, that's where we have a fault occur, where you're seeing movement of the rocks relative to each other. These aren't the type of vocabulary I'll test you on for sure, but the rate at which this movement occurs is called the slip rate. So one of the common things along faults like San Andreas, people look at a slip rate of 10 centimeters a year. As a result, they can look at the satellite imagery of how much the plates are moving in other areas, and they can identify locations along that average slip rate and see where there's stress is building up, or the rocks aren't moving very efficiently past each other, and that get an idea of locations that are most likely to have earthquakes, and once a sense of how much slip rates occurring along two plates, how much the magnitude you'll expect to see where that happens. The other term here, again, I won't test you on this, but I want you to think about is the scale is frequency is used to describe what scale of frequency is used to describe these activities, and usually, for perspective, these are in millimeters or centimeters per year. The San Andreas section moves relatively a lot, but most of the scale of this is in the millimeter to centimeter per year range. So for perspective, here when faulting does occur, the earthquakes, the amount of displacement can often be several meters, pretty much instantaneously. The rupture that begins in an earthquake scenario starts again at the focus, and it sort of propagates, in all directions along the failure of that plane. The key thing here, when you think about the Earth, is that if you're at the land surface, you start going deeper and deeper and deeper, there's more pressure from the overlying rocks on top of you. And as a result, in almost all scenarios in geology, wherever you're at a deep focus point, the area with the least amount of pressure is actually going to be upward. And as a result, you'll typically see propagation, according to the least compressive stress, or whichever the lowest forces are. But in many cases, that eventually is going to propagate up towards the surface because of the fact that pressure increases down. And then the key thing, I think everyone's probably heard the term before, but we're going to talk about a little bit, is introducing the idea of seismic waves. And seismic waves are basically the energy waves which accommodate this propagation of energy from the source out into the world. So, this is a perspective just looking at putting these all things together, looking at the earthquakes in the Bay Area near San Francisco, and basically combining various types of sciences, looking at the history of earthquakes, looking at the geodetic imaging of how the landforms are moving, but also looking at certain aspects like the amount of stress that's built up. You can actually look at a fault system through the San Andreas fault system here, where again, I've introduced the Hayward fault and others before, but you can actually look at each of these individually and they have a pretty good indication of the likelihood or the risks at which there's going to be, earthquakes over some period of time. And usually, this is a map that's earthquake risk between now and 12 years from now, 2032. But notice that if you're in this area, probably in the Hayward Fault line, right in the center of the Bay Area, is the most likely for it to occur. These are all sort of, almost like actuarial science, where you're trying to, think about it in terms of an insurance perspective, how likely it is going to occur and how likely it's going to be of a magnitude of certain degrees. And the USGS, as well as a variety of private foundations, but mainly the United States Geological Survey, will basically be responsible for creating these risk maps. So, for perspective, putting all these things together, places like San Francisco have about a 62% chance of an earthquake, of a magnitude that will cause significant damage in this time frame. That doesn't mean California is going to fall off into the ocean or anything like that, but it does mean there's going to be likely to be changes. So some more vocabulary around this. There's a term active faults, and an active fault, you'll see this appear in your worksheet for this week, is considered active if it's moved within the last 10,000 years. That's within the Holocene epoch, Holocene or Quaternary or Anthropocene epochs, which are the last 10,000 years. So for perspective, I think it's probably obvious to most of you that we don't have geologists out there with seismographs 10,000 years ago. So part of that is actually, looking at something called paleoseismology and determining where earthquake events occurred in the past and understanding the magnitude of those things as well and the timing of those. A fault that is potentially active, which we incorporate into risk models very differently than potentially active, but potentially active still is relevant to monitor, is if it's been active between 10,000 years ago and 2.6 million years ago. We'll talk about that more later when we get to volcanology. What's important about 2.6 is sort of a change in uncertainty of timing of a lot of events. And then something that's even if there's a fault that's present, something that hasn't been active in the last 2.6 million years is considered inactive. In reality, all three of these components tie into the idea of seismic risk, but obviously active is much more likely to occur than the others. So, for perspective, anything recent, more than less than 10,000 years is active. Anything within the last 200 years, where it's recorded by written record, this changes a little bit depending on where you're at in the world. That's considered historic. Okay, and then potentially active goes back through the Pleistocene, and beyond that, we can document the occurrence of major faults, but we don't really have major earthquakes and faults. We don't really have a lot of indications how likely they are to occur. So, what are all the factors that go into determining and assessing fault activity? The first one is actually observing tectonic creep, observing this plate motion relative to each other, and getting a sense of how much stress and strain are going to be present in the rock system. Okay, and a good example of this actually comes from the Hayward Fault in California. I showed you some examples of this, that the fault runs right through the stadium. What I didn't show you yet was that within the last 11 years, there's been about 1.3 inches of movement of the two sides of the stadium relative to each other. And this gives you a sense of, of course, they come along and they tar over this every often. This gives you a sense of the fault line that's developing as the stadium's moving past each other, where you can physically see what's occurred from this. This is actually deformation or related from the stress, deformation of activity along that fault. So in addition to the tectonic creep, the other one that's dictates how much risk or how much shaking we'll see in an earthquake is the magnitude. The more energy, obviously, the more shaking, the more likely damage is to occur. The greater the closer you are to the epicenter, the more the energy will dissipate close to where you are, and that goes back to the idea of the fact that in general on the Earth's surface, in the Earth rather, that the area towards the surface is going to be the least amount of force beneath it. And also, what's really important, and it's actually I think the most important lesson you can get out of this course on earthquakes, is what the local conditions look like. From a philosophical perspective, we can't stop the plates from moving. We can't stop the forces from driving and building up stress, and we certainly can't easily remove the stress so that strain doesn't occur. Okay, and in reality, we can't necessarily change what the soil and the rock conditions look like. But what I think is a really important aspect from thinking about this in terms of sustainability is designing communities and designing societies around those communities where we recognize the local risks, not just in terms of the frequency of active seismicity, but also in terms of the local soil and rock conditions, so we can avoid being in areas where if an earthquake occurs, damage will occur. I'll talk a little bit about what more that means in a second. But the key thing here is to recognize that these factors together actually, dictate how much seismic wave energy and shaking you're going to see, and as a result, allow you to predict how much damage is going to occur. So on this topic, there's sort of three primary seismic waves. There's P, S, and R waves. We'll come back to this. I will not include the definitions of these waves on the first exam here, but I certainly want you to pay attention for it for the second exam. And P waves are basically what are called compressional waves. It's waves moving together. Key thing is that P waves can move through solid, liquids, or gaseous materials, so they can be transmitted basically anywhere. The other thing is that these travel with a velocity of several kilometers per second. Okay, so they're very rapidly moving. And actually, P waves are detectable to human ear. So a lot of folks claim they could hear an earthquake before it happened, before they see the earth, waves, the seismic waves arriving. And I can tell you, when I was in Ethiopia one time doing geology work on a dam to see if the earthquakes in the area would allow us to put a dam on a river, or whether it would be a risk of flooding. We were actually out in the field walking down a road, and you could hear this noise like an explosion happen. And then, it actually felt like a few seconds later before the road sort of went up and heaved down and up and down from the actual damage from the seismic event. So these are often get out to people, much faster than anything. If they get out faster, often they are actually detected there beforehand. So the key thing is you can think about this as a spring, where you have a spring with a ball on the end of it, and when the way the wave works is by putting energy into the spring, and the energy is dissipated out through the spring. And this can come by pushing or pulling, but in all cases, P waves can propagate really rapidly. I'm gonna show a video here of how P waves work really quickly. So you notice here, these are transmitted very efficiently through the spring, and it can be by pulling it apart and letting that happen, or it could be by pushing it through, depending whether it's divergent, convergent, or the relative motion of the wave. The second type of wave is called a shear wave, and there are two important differences between P waves and S waves. S or shear waves, should have said P is a compressional wave. I did a primary wave, but these are compressional waves. Okay, so the P stands for primary. S stands for shear waves, and these can only travel through solid materials. And they travel about half the velocity of P waves. They're a lot slower. They'll arrive in an area later than the P wave. And the key thing is that these sort of only have up and down motions. This is what caused that road I was talking about in Ethiopia to look like a wave coming at me. They have to be at the right angle of the wave of propagation, so up and down, or sort of side to side, relatively speaking. And basically, you see is as the wave is, this is the epicenter over here, and the wave is migrating away on that spring, you would see that the S wave is sort of coming up and down. As a result, you can imagine that up and down wave can cause a lot more damage at the surface of P waves. So even though P waves have most of the energy, travel the fastest, and often can be heard, the S waves tend to do a lot more damage. I'll show you a video here to give you a sense of what an S wave looks like. So you can imagine at the surface, you can see where that's going to do a lot more damage, that wave action that you see at the surface, than a P wave. So just for perspective here, I'm going to go back and just really one time show you the P wave. Notice how much less surface energy, in terms of distorting land surface, is just to sort of see that shock wave come through, as opposed to when you see this large rolling energy at the surface. Of course, the magnitude of that wave and the frequency of that wave have a lot to do with predicting how much damage it'll do. The third and last type of waves, and this is where we'll end for the class today, are sort of called R waves. Those are the seismic waves that reach the surface. They produce really complex surface waves, which can really do most of the damage. They're slower than both P or S waves, or P and S waves. And in reality, even though S waves can cause a lot of damage in and of themselves, these are the waves that are really responsible for most of the damage associated with earthquakes. So these are, tied to the sort of complex, rolling motion that result in a lot of cracked walls, foundations, and most of the damage that causes buildings to sort of come off of their sort of mechanical strength and fail are related to the complexity of this non-orthogonal motion in these waves. And these key things is that if you think about this being the epicenter, the P wave transmitting like this, the S wave, having these waving motions, the R wave actually typically has a sort of convoluted, circular motion sort of within the waves themselves. So you notice they actually have this sort of counterclockwise in this example rotation, sort of without being well oriented to any of the other waves. So this rolling motion is usually in the opposite of whatever the direction is. In this case, it's counterclockwise, and opposite of the direction of the propagation of the primary or compressive wave, and also is opposite in terms of the direction of the vertical motion. So these are a bit harder to actually just show simple video of, but these are the ones that are just sort of chaotic and cause a lot of damage, and where the type of rocks and soils you have near the surface that interact with those types of waves really dictate whether you have a chance of surviving it. So some very brief idea here. S&P waves, timing, how long it takes between a P wave to arrive, and the difference between a P and an S wave, since the rates are known, can be used to actually determine that the epicenter of a given earthquake is X distance away. So for example, there's this background microseismicity almost continuously going on that I mentioned. The P waves, the P wave forms can give us a sense, okay, P wave arrived, we know this is occurring, then you actually can look at the gap between a P wave and an S wave here to get a sense of how far away this is. And by having multiple seismometers in different parts of the world, of the area in the world, you can actually use the relative distances to what's called triangulate, or draw a circle around your seismometer to know how far away it is, and tie that back to locations. And then with a group of seismometers working together, you can actually determine what the actual epicenter is, and use that to infer some information when you have more seismometers about the three-dimensionality of where the focal point actually is. The epicenter is usually what's easiest to detect by measuring the distance between those. So you notice here that in terms of the surface distortions, the P waves, where most of the energy is dissipated, are much smaller than the S wave. And then in terms of surface distortions, notice again that the R wave, even though there's much less energy there, the actual amount of distortion that occurs at the surface is significantly larger from the P to the S to the R wave. So even though the P waves, a lot of the energy, it doesn't really do much of the damage. The R waves, which we'll get back to in the next lecture after review on Wednesday, will tell us more about how this all works. So I'm gonna stop there for today in terms of the lecture. Just remember, the review will be posted this afternoon. We'll have a in-person review for everyone to ask questions on Wednesday, and the exam one will post basically at midnight on going into Thursday, and you'll have at least hopefully with 2 days you'll have an adequate amount of time to get the exam done. If anyone's any questions, any concerns, feel any more time or any accommodation for a certain reason, I'll be happy to accommodate. Just let me know. But we'll wrap up there, and thank you very much for listening along, and good luck with the exam. I got a question about the exam is proctored. No, the exam is going to be online. I'm gonna trust that you all will not cheat and take the exams yourself. But there's the exam's going to be online. Again, for standard, it'll be open for 2 hours whenever you start taking the exam. And as I did say at the beginning of the class, that it will be open note. I think it's easier just to make it open note than try to worry about people trying to spend their time finding creative ways to get the notes. We'll cover more exam questions on Wednesday, and also the written portion of the review will be up on the website, and this afternoon, and available for discussion on Wednesday. All right, thank you very much. I'll see you all on Wednesday.